Siddarth Arora. I'm scientist B at NIH NERC Guwahati. So my topic will be design flood estimation for DPR preparation. So how many, like, I think everybody is a civil engineer here, most of them. Okay. So I will brush through it. I will not go into details. So I'll brush through the topic. So I'll give you the guidelines at how to understand. So when we are preparing the DPR, so I think most of the topics have been covered up. So in that case, one of the important thing is how to get the design flood. So for any structure, whether you are building a culvert, whether you are building a bridge, or like for this we are doing anti-erosion measures. So we need a flood level and we need a flood velocity. So these are certain techniques for how to do it. So just a basic introduction, a flood is a relatively high flow system that overtops natural banks. So you have a river bank. So if it is overtopping that, it is inundating the area more than it is required to, we call it a flood. So design of hydraulic structures such as spillways, embankments, etc. require flood estimation to estimate the size and cost. Now you want to develop any hydraulic structure, you need to know that how much flow it is going to take. So that is why we need to have a design flood. Now for that, any structure to cost, as sir was showing in the previous, you need to estimate the cost of it. So the cost will depend on the size of it. The size will come through that how much hydraulic load it can take. So these are the type of flood. We have aerial flood, coastal flood, urban flooding and riverine flooding. So aerial flood is in which there is a prolonged rainfall and the river gradually swells up and the flood is of a larger duration. Urban flooding is what we see in Guwahati city, particularly because of either lack of drainage or improper drainage or because of any other reason. Coastal flooding is because of mostly sea intrusion, high tides and all. In this training, we are focusing mostly on riverine floods. So there are multiple methods. You have rational method, you have watershed models, you have flood frequency analysis and unit hydrograph method. So I will be focusing on two. One is a flood frequency and unit hydrograph. The other two methods I will not be undertaking, that will be undertaken up by somebody. So watershed models is one of the most common methods where we use certain hydrological models to identify what is the flood level, how much is the discharge, how much is the velocity. So that is on the computers. Before computers, how did we used to do that? We used to do it manually. So although now we do have computers, we have all the models, but it as a field engineer, we should be able to knowing that how to solve it on pen and paper. So that is required. So tomorrow, if you made a model on a computer and you gave some number, okay, the high flood level is 10 meters or 20 meters, or velocity is discharge is 1000 square cubics. As per model, it is looking okay. You have done everything. But when you solve it on paper, it will come out that, okay, it is not coming like that. So sometimes you have to verify it manually. So do not rely on the models entirely, whatever heck HMS, mic, whatever you are using. Don't rely on that whatever, because how the models we're using is we take some data, we input, model does some magic and we get the numbers. So for us it is very good. We don't have to do much of the thing, but we should be knowing what all processes are going inside so that if there is any error, it could be rectified or it could be caught at the preliminary level. Because DPR is an important government document, and if you publish something wrong in the DPR, eventually it is going to come back to you. So creating a DPR is a very cumbersome and a very specific process, so it should not have any mistakes. So do not rely entirely on models. At least do some manual calculations to verify. So I will be using, so first is the flood frequency analysis. I think everybody has studied during their engineering or during multiple training. So I'll just brush it up. So we are looking at the frequency of it. So you have a long-term data and you know what is the flood level, what is the weather. So what is the frequency of that flooding occurring on a repeated time or on what time scale? So we plot those probabilities along the flood on a log paper and you finally get a straight line or a curve from where you can estimate, okay, in upcoming time, if this is the flood level, this is how much it is going to be. So you can estimate it. It's not an accurate thing. Okay? It's an estimation. In reality, the number might be less than that, more than that. But generally, whatever the design flood criteria that we are using, we always incorporate a safety factor into that. So the maximum flood level and our design flood level will always be more than the maximum flood level that has been observed. So there are multiple methods. You have Gumbel extreme value, you have log Pearson, you have normal distribution, you have gamma distribution, then you have log normal, log gamma. Even in Gumbel extreme values, you have type 1, type 2, log Pearson, type 2, type 3. There are multiple methods. So I will only go in detail of the two methods, citing the time shortage. Now, these are the two most common methods that we use in Indian context. You can always use other methods. It is always a good practice that when you are designing, it is always good to have all methods included, because every method will give you a separate number. So how to determine? So suppose my Gumbel gives 100, this will give 95, this will give 105, this will give 110 as a design flood, let's say. Now which number to choose for design? If I choose 110, the cost goes up. Project might not get approved. 95, somebody might object, this is very low, it will collapse, you have to redesign it. So which process to use, that we will see in this lecture. So first we will go for Gumbel method. I will just lay out the specific steps. I will not go into theory, how it has come, why it has come. I'm not going to. So we are going to work, and so very specific works. So X is the magnitude of our estimated flood that we want to estimate. Small x is the magnitude of the mean flood value of the observed data. And delta x is the departure from the mean. So generally how we write it, so you must have been familiar with. So it will be x equals to x prime plus k into s. I think everybody can recollect that kind of method. So in that case, S is the standard deviation of the sample. We will calculate it from the data, and K is the frequency factor. For that, one chart has already been developed by CWC. We can directly refer to that. If you are more into it, you can derive it yourself also. So this is the procedure. First, you arrange the annual floods in descending order of magnitude. So suppose you have 20 years data. Okay, so 20 years, but it might not be consistent. It will be plus minus. So you rearrange it in descending order. So highest flood level goes to number 1, lowest flood level goes to the last. So you rearrange the data in that order. Then you start arranging rank. That is, we are doing it by the value called M. So 1, 2, 3, 4, 5, 6, you can always put it. So that is you ranking the flood level. Then you will calculate the return period and the probability of exceedance by the equations using n plus 1 by m and m by n plus 1. So once you have these numbers, so return period, whatever you are choosing, 25 years, 50 years, 100 years. So depending on the structure. So if you have a large hydraulic structure, you design it for 100-year return period. If you have a small hydraulic structure, you design it for 25 or 50 years. So for embankment purposes, we will be considering 50 years. 50 years return period. For safety side, you can use 25 also if it is a small channel. If it is a bigger channel, you use 50. Then once you have all these values, you calculate the x square, sigma x and sigma x square. So these are the mean values that you have been using. Now we calculate the mean, the squared mean, means of squares and the standard deviation S. So this is the procedure. So this is, you go step by step, life becomes easy in that case. So once we have all these parameters, so you have S, you have capital X, you have small x, x bar is the mean flood. So once you plug in it here, depending on the return period, whatever return period you are using. So if you are using 25 years, the K value will be different. If you are using 50, the K value will be different. So using these values, you can plot a curve and you can find out what will be my estimated design discharge in that. So this is the value of K depending on the return period and the number of sample size you have. So suppose you have 30-year daily data, okay, or you have 30-year monthly data. So it will be some 360 values. So you can check from the sample size, okay, that how much of flood is once a year. Okay, so you have 30 values in 30 year data. So for 30 years, and if you are using say 25-year return period, the K value will be 2.393. From where this table has come, I will mention that also. So this is a standardized table for Indian context that you can use. So it makes a life little easier. If you are interested, you can calculate the K yourself using statistical methods. which is also a procedure. If you have more time, you can always do that. It is always good to learn. So I'll give you an example. So this is a solved problem. So we have around 21 years of data and we have the flood peak. For all these flood years, we have the flood peak. So once we have this data, now I want to say that what is a 25-year return period flood, what is a 50-year return period flood based on this data that we will try to calculate. So based on this, first we arranged the peak discharge in descending order. We gave it ranks n that I told. Then we have to return the probability n plus 1 by m. So n is how much? N is 21. M value is this. So n is 21 plus 1, 22. M is 1. So first value is 22. Okay. Likewise, you can always compute this. Similarly, m by n plus 1 we will do. So m is 1, n is 21. So 1 by 22. Likewise, you can always get the values. Then you can get x square value. This is basically the square. Then you summate all of it. You will get this big number. So once you have this, so you have calculated the mean, that is the x bar. You have the squared mean. You have the mean of squares. Now, why we are calculating these two parameters, although we don't see it anywhere in the equation, that we need for the calculation of standard deviation. So once you have the standard deviation calculation, now you have the mean, you have the standard deviation. So x prime is there, s is there, k you have already seen from the table. And once you do that, what we can do is x equals to x prime plus kx. So based on that, you can always tell. So for 5-year return period, the k is this, 50-year return period, the k is this. And because this thing, the sample size, okay, this is linear 15, 20, 25, 30, 35, 35. So you might not have that. You might have 32 samples, you might have 29 samples. So what we do is, in that case, we just interpolate the values between these two numbers. Just imagine it as a straight line 30, 0.866, 35, 0.851. And if I need a value for 32, you can just simply interpolate between these two numbers. We can do that, right? Everybody is familiar with that. So once we have that, so you can get flood flow in QMAP for different type of return period. So this is the Gumbel distribution method. It's a very simple, straightforward approach. Now there are always variations in that. You can use log Gumbel, Gumbel type 1, type 2. In that, what the mostly things will vary is this K and the definition of S. The basic formula remains same. That you have mean plus minus the variation. So that is the flood. Second thing we come is, the most common is log Pearson type 3. Again, now earlier what in Gumbel method what we are using a simple straightforward method. Whatever numbers we take, we process those. In this case, we take logarithms on the values of our observed discharge, and then we solve the equations based on logarithmic parameters, and finally in the end, whatever value is there, so we will take the anti-log. So anti-log is, so suppose I like log 10. Log 10 equals to 1. Or if I say log 100, it will be 2. Okay, so what does it mean? So if I say that my value is 2, what will be the parameter? It will be 100. Everybody is clear on that? Log and anti-log? Or do I need to explain it a little bit more? Okay. So similarly, just like in Gumbel we saw, x prime, x equals to x prime plus variation in the standard derivative. So similarly, we are looking log qj equals to y bar plus kj into csy. This csy is the skewness coefficient. So what happens is, when you are fitting a number on a graph, we have a sample distribution styles, multiple. You have normal distributions, you have log distributions, you have gamma distributions. So it will always fit on a kind of a curve. So now the curve, we have a board, we don't have a board. So suppose you have a simple normal curve, you can divide it from the center line into two equivalent pieces. Now if the curve is little bit skewed towards one side, means you have a very quick peak and a long lag bar. in a hydrograph. So that is a skewed kind, that is left side skewed. Similarly, if you have a long rising limb and a very quick discharge limb, what will happen? It is on the right side skewed. So this skewness coefficient gives us that how much the curve is deviating from the center line. So that we will calculate. Now for these KJSY and CSY, these have already been calculated and put in a table for your making your life easy. You can calculate it yourself also. We will see the procedure. So skewness coefficient finally comes as A by SQ. Now what is A? A is the skewness. It's a mathematical term. Basically how much is the graph going here and there. So skewness comes by equals to n minus 1 by n minus 1 into n minus 1 2 into summation of xi minus xn. N is your total observed sample size. Xi is the individual sample value number. So like we have 10 values, so it will be 100, 120, 90, whatever. And xm is the mean of the whole data. So you subtract the observed value from the mean value, the mean value from the observed value, cube it and summate all of the data. Make one number. Summation of this into this factor, this will give us the skewness. Variance we have already seen in Gumbel method, it is a standard formula. Xi minus xn square by n minus 1. Now, generally, when we have a large data set, we use it as n minus 1. But if we have a small sample data set, then in that case, we use n. So, there is a threshold, particular threshold, when to use n minus 1 and when to use n. So, when you have a large data, this mistake won't make much difference. But if you have a small data, this mistake will give you a random, very big mistake and it will overestimate or underestimate your design. So you please keep in mind that when to use n minus 1 and when to use n. Okay, so there is a standard definition of that, you can always check. Then when you have these two parameters, just calculate the CS. So now you have the CS, you have the KJ value, you have the Y bar value. Just plug into the equation and you will get all these. So this is the frequency factor for K in this for return period and skewness coefficient. So skewness coefficient you have already computed. Okay, these are the values. This is the probability of exceedance. This is 1 minus 1 by t. This is not 1 by t. Okay, so remember that. So you have return period, you have probability of exceedance, you have skewness coefficient. So based on this table, you will get the K values. So once you have the K values, you can use this method. Now, as I told that we are using multiple methods. Okay, some will give you less, some will give you more. So which method to use? Which value to use? Okay. So somebody will ask why we are using 100 Qmax and not 120 Qmax as per your design flood calculations. So in that case, something called D-index test that we'll be using. So in D-index test, it is 1 by U bar summation of xi minus xi star, and this is the modulus of it. Now modulus means that you have to take the positive value. If this sum is minus 2, you just put 2. If it is minus 5, you just put 5. Okay, you just take the value of it and not the sign of it. So once you just put, so in that case what you do is, whatever the 6 maximum values you have in your data set, you choose those and xi becomes that. Okay, so the 6 maximum values that you have. Then xi star is the corresponding value that you calculate by this log Pearson method or Gumbel method. What is the return period of that flood value? What is in that case? So it is 25 years, 50 years, 30 years, 100 years, whatever you are using. What is the corresponding value for that particular? Once you solve this, so this number will around somewhere between 0 and 1. The more closer to 1, we choose that value. So suppose you do the D test for all this, you have values of 0.5, 0.6, 0.7 for different methods. Whatever is giving you 0.7, you choose that. Okay. So this is a practice problem. So although now we have less time, so otherwise I would have asked you to solve it. Uh, so you can always do it on the practice side. So this is for your training. In that case, you just try to solve the 25-year, 50-year, 100-year return period using the Gumbel and log Pearson method. If you want, you can always use other methods. It's easily available online. So please solve this, and I think there will be some assignment is provision is there. I will ask them to for you to submit this assignment in the evaluation. Once we do this, you will get multiple values. Then we do the D-index test and come up with that. Okay, we will be using this. We have used this particular type of method, Gumbel, log Pearson, normal, or whatever you have used. And this is my design flood for 25, 50, and 100-year period. So please do that. Now, one thing that we have is, although now we can always use it solving by pen and paper, you can use Excel also. Okay, so it will save you some time. So the manual calculation can be done by Excel or in calculator or some software. But always remember what the method is, so that even if required, you can do it by hand. So that we should be knowing that. Now second comes is, now this method is when we have the discharge data. Now we are coming to a catchment which does not have any gauging station. Now what to do? Oh, like we have multiple, we have particularly small catchments. If we see like particularly in the BTC area, most of the like Manas is there, Beki is there, although they have some gauging. Yes, Manas, like some tributary of Manas. So now you have some tributary of Manas which does not have a gauging station but is having a erosion and flood problem. So how to calculate design flood in that? So what to do? Now we don't have any data. So what do? We generate the data ourselves to do the calculations. So that is what we call it as synthetic unit hydrograph. So in synthetic unit hydrograph, what you do is, in case of ungauged basins, you use a set empirical relations which have been derived from observation over the years by multiple scientists, by multiple engineers. I think everybody has heard the name of Khosla formula for irrigation and all. So Khosla formula is basically an empirical formula which was developed by one chief engineer called Khosla. He was in Punjab irrigation before independence, 1930s. So all the irrigation channels in Punjab region have been designed based on his formula. So what happens is, when you are using empirical formulas are always developed based on experiments and observations in a particular area. If you try to implement that same formula in your region, it might not work. So you might have to modify it a bit. So now you have like Kc power 1.6. So it might work in Punjab, it will fail in Assam. You might have to adjust those formulas. So you keep that in mind. So this kind of troubles we are facing, the CWC came up with the novel idea. They were like, we will use the catchment properties to derive it. So because catchment properties are unique, and on the basis of it, if you derive something, so it will fit everywhere. So one solution fits all. So we'll be using that. So one of the most common methods is Snyder method, that I think everybody knows or have used. So in this Snyder method, these are the important things: duration of excess rain, basin lag, peak discharge, base time, width of the unit hydrograph. So these are the important factors that we need to compute based on the data available from the catchment geometry. Whatever the catchment geometry is, we have to use the data from there. So this is some specific, I won't go into detail, won't bore you with the mathematics of this. So Tp is the peak flow, Tr by 2 is the unit duration, half of it, this is the lag time, this is the total base time. W75 is width of the hydrograph at 75% height. W50 is width of the hydrograph at 50% height. So once you start solving, you will get these 5 points and you have these points. So you can fit a curve manually in that. Okay, so in that case, sometimes you might have to adjust the curve little bit plus minus to get you the desired value. So once you have these, you can always design your hydrograph, and once you have a unit hydrograph for your catchment, you can always compute the discharge at a location, that how much it is coming. But the technique is, suppose in the river basin you want to calculate at 3 different locations. So you will have to recalculate the unit hydrograph for these 3 different locations because the catchment properties will change. The catchment area will change. Okay. So this is another more of mathematics. You can always refer to the books in that case. So coming to the Indian practice. So Indian practice, so CWC has divided India into around 26 zones. Okay, so in Northeast there are particular three, 2A, 2B and 2C. Okay, so if you are working in Assam and North Bank of Brahmaputra, you come into 2A zone. So Assam and Arunachal will come in 2A, Nagaland, parts of Manipur and Meghalaya will come into 2B, Mizoram, Tripura and all, they will come into 2C. So all these zones have different parameters, different characteristics, different formulas. So please ensure whatever catchment you are using, okay, you ensure that which catchment is lying in which zone. Okay, if you use too big of formulas in 2A, everything will be wrong, okay, and the DPR will be rejected based on technicality. So don't do that. Now the catch is, I cannot use this formula for Brahmaputra basin. Okay, it has to be used only for small catchments, that is up to 2500 square kilometers. If your catchment exceeds this method will not work. Okay, so don't go, because if somebody catches that you have applied these formulas for other than this, okay, you will be in trouble. So don't do that. So this is the QR code. You can always scan it through your phone and you will get the manuals for each of these regions. Okay, I'll share the PPT, you can always have. So 2A have a different manual, 2B has a different manual, 2C have a different manual. This is not one file. So please ensure. So I will take a case of Pagladia River in BTC area, the Bodoland Territorial Region. Now this area, it does not have many, the specified area does not have multiple gates, any gate site. So but we have to do, because the erosion problem is quite significant in this region. So anybody from Assam, WRD? Huh? Yes, so I think you might be knowing the erosion problems in Pagladia, might have heard about it. Yes. So this is a very significant problem in this region because you have high flow coming from Bhutan and suddenly it gets into plain, the river gets widened. So erosion problem is there. But we don't have any gauging stations. Now if we have to do any embankment work, so a DPR has to be prepared, it has to be approved and all, how to do it. So what we do is we finally, using GIS, I think everybody is familiar with GIS. ArcGIS, QGIS, everything. You have done basin delineation and all. So once you do that, so the software calculates these parameters for you. Yeah. If you are more interested, you can always take the contour maps, design yourself, okay, and start doing geometrical analysis to get all these parameters. If you have time, you can always try it once. I think we have done that during plane survey table and all that. So once you have these all parameters, all these parameters are based on the catchment shape. Hence, this formula will work everywhere. So let's see how we are going through it. So first is we make a unit hydrograph based on the catchment parameters. So you have all these parameters. You have QP, TP, W50, W75, WR50, TP, TM, QP. Everything is there. And you come up with all these numbers, and these are the units of it. Okay, so please ensure that because these are empirical formulas, okay, the parameters, the equations you might get, sometimes these will have different coefficients because they are using imperial units. So imperial units is cubes, feet, seconds. But if we are using metric units, that is seconds, kilometer, meter, and all those, and cumex, meter cube per second. So ensure that whatever units that you are using, okay, that you are appropriate. Because if you are using data in cubes and feet and you try to implement all this, the values will go haywire, everything will be wrong. So there is a very simple example of this. NASA spent more than around I think some $500 billion on one space probe. Because US they use imperial units and Europeans they use metric units. There was a confusion, and after the launch the spacecraft just got lost. They could not contact it. So that is how small, just not giving attention to what units you have, you can have large disasters. So don't do that. So based on that, we are able to develop a unit hydrograph, and we have all these ordinates, and our base time is total 29 hours. Now, based on this catchment, and 29 hours is not the standard practice, so we reduce it to 24 hours. The unit hydrograph has to be made in a 24-hour duration. So basically into that, so we convert that into 24, and just to check whether our unit hydrograph is correct or not, you do a simple calculation, that is A into D by 0.36 TR. Okay, so this is the estimated peak value of the discharge. So A is the area of catchment, D is the rainfall amount in centimeter, TR is 1 hour because it's a unit hydrograph. So you plug in these values and you compute a number. So as we for this we have computed as 1055.6. Now if you add all these numbers, the UG ordinates, okay, these units, so this number and the UG ordinates, they should match. Okay, there might be a little variation because if you add all this, you will come up with the number of 1056. Here we are having 1055.6, so it's close by. It has to be very close match. It cannot be like that you are having 1056 and there you have 105. It cannot be like that. It has to be very close. Because it's a mathematical operation, some significant small errors are okay, but not large ones. So, whenever you derive a synthetic unit hydrograph, match it with this value. That is required. Okay. Now then, we have now, because we don't have any gauging stations, we don't have any rainfall data also. So IMD publishes maps, okay, which gives you a rainfall estimate. It's called isopluvial maps. Okay. So you have map, different variable kind of map: 5-year, 15 minutes, 5-year, 1 hour, 5-year, 2 hour, 5-year, 24-hour rainfall. So based on this area, what you see the isopluvial map, you will get the value of 32 centimeter for the BTC region. So in 1 hour, now it is we have to compute it for the overall area. So you have something called 0.2 aerial rainfall ratios, that is from the CWC manual. Based on the area and based on the duration that you want. Okay, now I have 50 and 24-hour rainfall. I want to convert it to 50 and 1 hour rainfall. So it is not that you divide by 24, it is not the way. You multiply it by a factor. Okay, so the factor you computed from here. So our area is, I think, around somewhere 350 or something like that. Yeah, so we are using this value, directly multiply, and you get the value for 1 hour. Okay. So this is a description of isopluvial maps by IMD. So you can see, I think the image is not very clear in this case. So like this map is 100-year 1 hour, this map is 50-year 1 hour. So you can see in that case how the isopluvial maps they have worked. So these are in public domain. Okay, every department has a copy of it. Okay, IMD maps, these are published almost on every year. They are mostly same, but you can always keep a copy or you can get it from IMD itself. So like for this northeast region, you have 50 and 24 rainfall, you will have something called 810C. So that is the sheet number. So you can see in that case, likewise here, we have 320, this one region, you can always get to the value of that. So this is an estimate of the rainfall. This is not an actual rainfall, this is an estimate because we don't have any gauging stations. So we are estimating based on the records, whatever we have gotten from the past. So now we have design storm is for 24 hours. Our catchment for design storm is 29 hours. So we readjust the value. Okay, that is 1 hour rainfall and distribution coefficient. So distribution coefficients are like this. So this is all in the CWC manual. You can always check these values. So just multiply and you will get the decrement rainfall. Okay. So once we have that, now we come to, now because we are using calculating runoff, we are calculating, so we have to take into account the amount of losses. So one is the design loss. So that is as per CWC guideline for zone 2A, it has been fixed at 0.24 centimeter per hour. Okay. Now for estimation of base flow, again because we don't have any value for it, so for zone 2A it has been fixed at 0.05. Now what happens is you can always, for the calculation of base flow, there are always multiple methods. You have separation, base flow separation from the hydrograph. You can always use that. But this is the standard method that we will be using. Okay. So once you have the rainfall, you have the design loss, you have the effective rainfall, now you have the effective rainfall graph for 24 hours. So this is the tricky part here. What you do is for the estimation of the peak flood, the rainfall excess units were rearranged against the SUH ordinates in such a way that the maximum rainfall excess unit was placed against the maximum SUH. Now what does this mean? Now you have all these rainfall values. The maximum rainfall value will be multiplied with the maximum ordinate value of your hydrograph and so on. Okay, the lowest value of the rainfall to be multiplied with the lowest value of SUH, highest value of rainfall to multiply with the highest value of SUH, and you have to go through it. This is directly from the CWC manual. Okay, these instructions have to be followed very clear cut, because if you deviate, lot of errors will come into picture. So once we see that, in that case, you will have direct, you have 1 hour rainfall excess, you have ordinate, you multiply it and you get this value. Now, whatever plate you are using for your hydrograph, if it is 100 years, so all these parameters will come for 100 years. So we implement for that. So you finally get a value. If you are using 50-year plate, so all these parameters, rainfall, effective rainfall will change, your distribution parameters will change. So whatever year flood that you are using, you have to design it for every return period. So if you are using a 50-year period, you have to design a separate SUH after the coefficients. 100 years, it will be separate SUH, and the calculations will also be separate. So once we have that, based on the point of interest. Now as I told, if you have multiple points in the same basin where you want to work, you will have to design your hydrograph for each of that point. Because as you go downstream, the catchment area is changing, the catchment boundaries are changing, the catchment shape is changing. Okay. So this is there. Then this is another method. It's called a simplified approach. So although it looks very simple, you don't have to do much. Okay, you have 0.762 into A is the area, L is the length of that, LC is the centroid length, S is the slope, and R25 is the 25-year rainfall that you are taking from the isopluvial maps. You can always just use these formulas to compute 50-year return period, 100-year return period, but this is only for verification. You cannot use this for your design. For design, you have to do all this method, and this is just a check on that. But whatever you have done, it should be coming around these values. Okay, so this is not a design value, it's a check value. So once you do that, you will get all these values like this. So for further reading, you can always refer to these textbooks. One is Venti Chow, it is applied hydrology. This is mostly used for master students. So this is a very good book and have a very good description of if you want to do every process manually. For Indian practice, I think you are familiar with this book, Engineering Hydrology by K. Subramania. So this gives in Indian context, and this book gives you a general overview of the hydrology. So both are very good books. I will recommend that you should have both the books with you to refer when you are working for DPR. Then these are the two manuals that we have to follow. We cannot deviate from this method, these two manuals. So one is the estimation of design flood peak, that is by CWC 1973. I have put the QR code. You can scan and you can get the manual. And then you have hydrometeorological zones of India, CWC 1981, that you give 2A, 2B, 2C. So just scan the code, you will get the URL, and you have a list of all these books. So whatever is written in these two manuals, we have to follow it to the word, line by line. Do not deviate from that, because any deviation from that will give you errors and it will raise question marks. So if you have followed these procedures, you can always go and say that I have followed this manual step by step. Nobody can question you. If you start doing yourself, then you have to justify that why you have done yourself. So this is the easier part. Obviously, you can always put on your brain, you can always do some little bit hard work, but not to deviate from these two manuals and whatever the principles are in these two books. This is our, मतलब ये मान लो कि ये धर्म ग्रंथ हमारा यही है, ठीक है. Whenever we are working on design flood, these are the 4 books that we have to refer. Anything outside it is not required. Okay, so that's from my side. So any questions, any queries, any clarifications? No. So all right, thank you.
Thank you, Arora ji.
Thank you.
एक रिसर्च बोलता है कि जो भी हम लोग सीखते हैं पढ़ते हैं उसका 70% 24 आवर्स के लिए वाइप आउट हो जाता है और 90% उसका विद इन वीक वाइप आउट हो जाता है. तो व्हाट शुड वी डू? तुम रिपीटेडली हमें इसको रेफर करना चाहिए. So that is why Nehar is providing all the links on YouTube also. You can refer it whenever it required. All the PPTs are being given to you in the WhatsApp ID. So in addition to do some more work. So from tomorrow is our visit. So day after tomorrow, what we do? From all of you, some 2 or 3 volunteers will come on the stage. और जो भी आज पढ़ाया गया है उसको 15-20 मिनट में ब्रीफ करें. Any 2-3 volunteers. The whole day session will be recapped in the 15 minutes to just polish your understanding. Any some from Assam, one from I hope from Arunachal. आपके पास टाइम है, आप you can refer the PPTs in the night. Just 15 minutes में आपको ब्रीफ करना है कि आपने क्या समझा. कोई भी नहीं है, मतलब ये ट्रेनिंग हमारा बेकार जा रहा है क्या? अरे इट इज यूजलेस. अरे आना चाहिए आप में से कि आई विल डू दैट. वही चीज फायदा है.
फिर ये कहाँ पे सेव करूँ मैं?
इसको डेस्कटॉप पे डाल दीजिए.
डेस्कटॉप में कोई फोल्डर है?
यहाँ डाल दीजिए.
ठीक.
वॉलंटियरली असम, Arunachal.
So in this aspect, there is a one practice problem that I have given. So I'll recommend that you, when you are in the evening, to try solving that yourself. Okay.
तो कोई भी नहीं है मुझे. आप करेंगे मुश्किल है हमारे. I have some limitations. नहीं बहुत ज़्यादा नहीं, कुछ की पॉइंट्स जो हमने एक पूरा कवर कर ही नहीं सकते.